Okay, this should be the last chapter of the course, and this is broadly on climate variability and change. So we will just run through all the time scales of climate change and talk about the dynamics of ocean and atmosphere associated with them, with somewhat of a specific focus on feedbacks, because as we will see, it's the internal feedbacks that take the solar radiation coming in and produce a very rich spectrum of time scales. Okay. There are some big names. Milanka, which always comes up, was the first guy to mathematically formulate the changes in Earth's orbital parameters, as we will see later. The glacial, deglacial cycles, or ice ages, ice age cycles are referred to as Milankovitch cycle. There was James Kroll before him, much before him, who also had similar ideas. Jakob Birkness is famous for his work on El Nino related feedbacks. He was the son of the famous Wilhelm Birkness, which we had talked about in the previous chapter. We'll see what Jakob Birkness did that makes him a very important person at the short time scales of interannual variability, specifically El Nino. So there are these whole range of timescales of climate variability, going from weathers which occur on hours and days, land surface going from days to months, ocean mixed layer, just the surface layer is along the same timelines, sea ice begins to get into years, volcanoes which are very episodic, vegetation, you can see it begins to go into million-year time scale because it has feedbacks and it moves slowly, it has memory, and so on and so forth. There are many ways to say it, but we will see what we mean. Thermocline, so ocean can be split into surface layer, thermocline, and deep ocean, which produce very different time scales. Mountain glaciers, deep ocean, ice sheets, orbital forcing, that's the Milankovitch cycles. Tectonics, we will see how continental drift has had big impacts on climate as well. Weathering is the geologic timescale control on carbon dioxide, and of course solar constant, which happens on monthly to yearly and decadal and all the way to billion-year timescales. Okay. We will learn about El Nino, which is the most dominant variability from year to year time scale, so-called interannual variability, is related to the things we have already looked at in terms of upwelling in the east, cold temperatures, piling up of water in the west, warm temperatures, sea surface temperature gradients. Because Coriolis is low, you also have wind response, pressure response, and we have of course deep convection here, and the local zonal circulation, which we didn't talk a lot about. We always talked about zonal mean meridional cells, but there is a very important zonal cell that becomes very important. We'll touch on paleoclimate at various time scales. There are these periods we will talk about pre-Cambrian. Cambrian is around 540 million years ago, when there was a huge explosion of new species. Before that you had Hadean, that's Hades, hell in Greek, and Hadean is when there was bombardment, primordial soup, not any evidence of life as far as we know. Archean comes from Arches, which means the beginning, where we get the earliest evidence of biotic elements in the rocks and so on. And then you get Proterozoic, which means early life. And then you get Paleozoic, and then Mesozoic, Cenozoic. We are now typically we keep saying Holocene, but the new geologic era has been defined beginning in at the Industrial Revolution, and it's now called Anthropocene. So we will talk about what's happening in the Anthropocene. Okay, so let's see the climate over Earth's history. Obviously has feedbacks from volcanic forcing, solar forcing, the feedbacks between a solid Earth on long time scales, continental drifts, and so on. Carbon dioxide, we will see, plays an important role at pretty much all the time scales that we will look at. So this is estimated change in the CO2 concentrations and net forcing in terms of CO2 plus sun. We already talked a little bit about greenhouse gases. We'll talk a little bit more. Obviously, they are trapping the outgoing long wave and adding to the radiative forcing, which is critical when we talk about climate change. So you can see there are various evidences of how CO2 has changed over time. So our CO2 of 10 here means that concentrations were 10 times the present day level. So you can see that concentrations have been as high as 20 times the current levels and down to the present level now, but we are increasing with human activities. So why do we have to worry if CO2 was so much higher before? Obviously because we were not around, so we don't know what our limitations are in terms of dealing with CO2 increases and global warming. Ice extents vary with the radiative forcing, so you can see when CO2 forcing is low and solar radiation is low, you get much larger ice extents in terms of latitudes coming down to excuse me, 30-degree latitude. And there's been also times when there have been so-called snowball Earths where the ice was probably down into the tropics. Okay, so there are issues to worry about. If you have to bring ice down to that deep into the tropics, then you have to explain how marine biology would have survived and what kind of feedbacks would have occurred to make the ice grow so far into the warm latitudes, right? So we look at all those things and hopefully my voice doesn't give up on me, and should be fun. It's a longish chapter because I'm going to cover all the time scales and not rely on the topics followed in the book. I'm going to give it a much broader time scale and more details because it's generally useful to set you up for global warming and so on.